Okay, so we have already talked about now limits and how that relates to continuity. And now we're going to talk about average rates of change. Perhaps you've heard that calculus all comes down to really two things, derivatives and integrals. So this is going to get us two derivatives, the combination of this kind of continuity and rates of change thing. So an average rate of change is where, like you just know, at some point the value was this, at another point the value was this. So what was the average amount they changed per unit during that time? So this is actually just the slope of a line, but it's a line that goes through 2 points on a graph, not the whole graph. So let's say that, that's bizarre, okay? Let's say that you have, this is your function. Then if I'm looking for the average rate of change between here and here, I ignore everything in between. I'm just looking for the slope of this line, which I can't draw because somehow I've got things crooked here. And the slope of this line, it would be called the secant line. So a secant line is a line through 2 points on a graph. So say x, f of x, and z, f of z. So just any 2 points on the graph will have their own secant line, and the slope of that is the average rate of change. Okay, so if we're looking at this, we don't know what the function actually is. We just know the value at 0, at 30 minutes, at an hour and a half, 2 hours, 2.5 hours, and 3 hours. We know how far we've traveled at each of those stages. So if we wanted to know our average speed, then we would take the distance we'd traveled and divide by how long it took us to get there, right? So this is just goes back to the distance equals rate times time. So rate times time is distance, divide by time on both sides. But in this case, we're not going a constant rate, which there have in your previous problems when you had the d equals rt, you had a kind of set rate. And we don't have a set rate, we have an average rate. So we're just looking for the average. So the first question is, let me get that one. And this one. So we want the average speed over the first 3 hours. So the question is, I don't know why I'm getting so crooked here. How far did I go? And how long did it take? So over the first 3 hours, that means it took 3 hours. So 3. And the first 3 hours is here. So I went 138 total miles. So I started out with 0 miles and I ended up with 138 miles. So I traveled 138 miles in 3 hours. So that's 46 miles per hour is my average, unless I'm misdividing. Okay, then the second question is, what's the average between a half hour and 1 hour? What speed did I average during that more specific time? Okay, so in this case, I can't just say divide by 3. And you're going to say, well, you divide by a half, because it's from a half hour to 1 hour. But the more kind of formal way to do that would be to say end time minus start time. So that's how you think through it to get it. But to build up to a kind of general formula, we can write it in this manner. So at the end, I've gone 1 hour. At the beginning, I'd gone half an hour. So their difference is how far I went, or how long I went. Then for the distance traveled, because we're still on a distance over time kind of situation, by the end of that 1 hour, I had gone 55 miles. But at the beginning, at that half an hour, I'd already gone 30. So I went 25 total, but that's found by subtracting the end point from the beginning. So 25 divided by 0.5 is 50 miles per hour. There's really an m over here and an h over there, so that's miles per hour is miles per hour. Division means per. So the one that we just did then, we had I shouldn't have deleted that yet. We had the function value at 1, 55, minus the function value at a half, 30. So f of the endpoint minus f of the beginning point. And then we had 1, our end time, minus 0.5, our beginning time, which is our endpoint minus our beginning point. So this is the slope of the secant line. And it's always just y1 minus y2 over x1 minus x2. We're just noting it differently because it's on a function graph, and the line is not that graph. So we're just pointing out that these 2 points, while they are points on the secant line, are actually points on the graph of f as well. Okay, so if we want to do this one, okay, so we want f of b minus f of a. I'll write this once or twice. I won't keep writing it every time. So this is f of 2. That's where I would normally start. Minus f of 1 over 2 minus 1. So I'm just plugging in the endpoints. You can do it in the reverse if you want to. It doesn't matter if you do 2 then 1 or 1 then 2. They just have to match, just like when you did a slope of a line in algebra. Okay, so this is, now I'm going to plug 2 into f. Square root of 3 times 2 minus 2 minus square root of 3 times 1 minus 2. So I've plugged in 2 and then I've plugged in 1. And that's over 1, 2 minus 1. So I can forget about that now because it's just 1. So this is square root of 6 minus 2 minus square root of 3 minus 2, square root 4 minus square root 1. So the average rate of change between x equals 1 and x equals 2 is 1. Now, instantaneous rate of change is when we start kind of getting our hands around the derivative. So now we have that a car starts from a stop sign and moves along a straight road. So they are going to increase in speed so that their position is given by 3t squared. They're not traveling linearly, they're speeding up from a stop sign. T is time in seconds, and S is given in feet. So we want to estimate the speed of the car at the exact moment of 10 seconds by finding the average speed first just between 10 seconds and 10.1 seconds, and then 10 seconds and 10.01 seconds, and then 10 seconds and 10.001 seconds, okay? So I'm just going to get this part. Okay. So I need, generally speaking, remember that what we're doing is f of b minus f of a over b minus a. So the first one, f of 10.1 minus f of 10 divided by 10.1 minus 10. We can go ahead and say f of 10 is 300. It might save us time to not kind of calculate it over and over. So in this case, we're going to have f of 10.1 minus 3 times 10 squared is 300 divided by 0.1. And then on the next one, we'll have f of 10.01 minus 300 over 0.01. I probably shouldn't have taken up so much space. And then we'll have f of 10.001 minus 300 divided by 0.001. Okay? So when I go back to the calculator then, I'm going to do 3 times 10.1 squared minus 300 divided by 0.1. 60.3. And then I'm going to do 3 times 10.01 squared .03. I think we could probably make a guess on the next one, but let's go ahead. 3 times. I have too many zeros. $60.003. So we started with 60.3. We next went to 60.03, then 60.003. We can probably guess if we went 10.0001, we'd get 60.0003, and so forth. So the closer that I get to 10, the closer this is going to get to 60. Good grief. The closer I get to 10 for my second t, the closer we get, the average rate of change is 60. So here's what's happening. I have actually a quadratic, right? 3t squared is quadratic there. That's pretty terrible. So let me kind of zoom in on the bit about 10. So here's 10, and this is around 300, right? So let me kind of zoom in on that. That's already fairly linear. But let's assume that I'm right here at 10. So what I'm doing is I started up here and took a secant line. And then I got a little closer and took another one. And then I got a little closer and took another one. And my end goal is to have an instantaneous rate of change, which is this line that's just at 10. And it's sort of like if you were running along here in zero gravity and you let a ball go, which direction would it go? It would go along the tangent line from either direction. I could run this way and let it go, or I could run that way and let it go. You can see it a little more clearly maybe if it's more curved. This would not be at 10, it would be fairly straight. But so if I'm running along, let the ball go, and it's going in that direction, and the secant lines, as you get closer and closer to this line. So if we let this get arbitrarily close, then the slopes of those secant lines would get closer and closer and closer to the slope of this line, the tangent line. So we're looking at a limit. The limit of these slopes is the slope of this line, if it exists. Has to exist from both sides. So the limit of the slope of the secant lines is the slope of the tangent line if that limit exists. So this is actually the definition of a derivative. So here's this image. We're starting with 10, and we're going to 10 plus something. So 10 plus h just means not 10. You could argue that the h is 0, but we're going to divide by it, so it's not going to be 0. So any value other than 10 is 10 plus h for some h. 11, h is 1. Negative 12, h is negative 22. Just any value in the world, you can figure out its difference, its distance from 10, and you can solve for h. So 10 plus h just means not 10. But we want to get very close to 10. So we want our h's to be small, but not 0. So we have an h of 0.1, then an h of 0.01, an h of 0.001, an h of 0.0001 would be next, and then 0.0001, and so forth. Or it could be 0.002. Just as long as it keeps getting smaller, we will keep getting closer to the instantaneous rate of change. So the instantaneous rate of change is what happens when you take these secant line slopes, and let me come over here and just note something real quick. We have A and some other point. So we're looking for the instantaneous rate of change at A. So we take A and we take somebody who's not A, and then we take the slope, so f of A plus h minus f of A plus h minus A, but then the a's cancel, and we end up with this. But we want to keep getting closer and closer and closer and closer to A. So getting closer and closer to A means h is getting smaller and smaller. In particular, h is going to 0. Okay, so this is called the slope of the tangent line. It's the limit of the slopes of the secant lines as the points get closer and closer to the value A. Okay, this is also called the difference quotient. You've seen this before, not with the limit, but just the f of A plus h minus f of A over h bit. That's popped up before, and it was called the difference quotient. So here's more of what I was kind of trying to sketch before. You really should be going from both sides, but it ends up looking crazy on a graph. Okay, so if we want instantaneous velocity, velocity is rate of change. It's not exactly speed, but the only difference is that velocity is signed. So speed is always positive. Even if you're falling or going backward, it's positive. It doesn't consider direction. Velocity has orientation. So if you take the absolute value of velocity, you get the speed, but velocity tells you which direction you're going. So this is finding actually the instantaneous, the speed at 10 seconds, because this is positive around 10. But let's bring this over here. Okay, so what we want is the limit as h approaches 0, that's the beginning, of f of, in this case, 10 plus h, because we're being given the a value, minus f of 10 divided by h equals 3 times 10 plus h squared minus 3 times 10 squared, we've already done that, but I'll write it that way this time, over h. Forgot to write my limit. Now, I've told you before, when you see polynomials over each other, which this is, to try plugging in first. But if you plug in with h in the bottom, you already know you're going to get 0 in the denominator, and it's problematic. You're also going to get, because if you put in h, this is just 10 again, and for any a that's true, you're also going to get 0 on the top. So you're always in a situation where you have a factor of 0 on top and bottom. So your goal becomes get the h out of there. So this is the limit as h approaches 0 of 3 times 100 plus 10h plus 10h plus h squared minus 300 over h. So that's 300 plus 60h plus 3h squared minus 300 over h. At this point, I can cancel these 300s. And generally speaking, at this point, you can always cancel everything that doesn't have an h in it. If you can't, you made a mistake, and you need to go figure out what you did. Okay, so this equals limit as h goes to 0 of, I'm going to factor out an h on the top, because remember my goal is to get rid of it, and now I have one everywhere. So 60 plus 3h over h, and now I can cancel these. So the limit as h goes to 0 of 60 plus 3h, and now I can plug in. So I plug in 0 for h, and I get just 60, which is what we thought it was at any rate, but now we've proven that it is. Okay, so now we want to do this here. I think the best thing to do would be for you to pause this and attempt to do this problem, see what happens, and then come back to see if you did it correctly, or if not, where it is you went wrong. So limit as h goes to 0 of f of 1 plus h minus f of 1 over h. So now I plug in 1 plus h for t. So that's 1 plus h squared plus 2 minus. F of 1 is 1 squared plus 2. Be careful and make sure that you subtract the whole thing if there's more than one piece. If you just write minus 1 squared plus 2, then you're going to end up with the wrong constant over here and things won't cancel. Oh, criminy. My limit back, okay? So that's the limit as h goes to 0 of 1 plus 2h plus h squared plus 2 minus 3 over h. 1 plus 2 minus 3 cancels. You can take another step to make that 1 plus 2 into 3 if you want, but anyway, they cancel. So this is the limit as h goes to 0. And now I just have these two pieces. I'm going to factor out an h, 2 plus h. So the limit as h goes to 0 of 2 plus h. And now I plug in 0 for h, and I get 2. So again, what this means is the slope of the line that's tangent to this graph f at t equals 1 is 2. Okay, so this brings us to how this applies to, well, one of the ways this applies to business is that you might want to find the maximum profit. You might want the maximum revenue. You might want to minimize cost. It all depends on what your goal is. But for that, we kind of would want to know what is the cost or the revenue or the profit if I make one more item than how many I've made right now. So you kind of want to know the instantaneous increase of cost, revenue, and profit, or decrease of any of those at a given level of production. So we consider the marginal cost, marginal revenue, marginal profit. And what it always is the instantaneous rate of change. So the marginal cost function is a function where when you plug in a production level, what it spits back out is the instantaneous rate of change of cost at that moment. Okay? So if this is our cost, for manufacturing X sailboats, this is our cost. And we first want to find the exact cost of making that 41st sailboat. So we take the cost that it was to produce the first 40. And then we take the cost of producing 41, and then we subtract them, and that'll tell us what our cost difference was between producing 41 and 40, and that's the cost of the 41st sailboat. So C of 41 minus C of 40 . Maybe I should do this in stages here because it's going to look like a mess. Okay, I switched colors. C of 41 is $11.79.75. Cost of making 40 boats is so the difference is 1179.75 minus 1175 is $4.75. I'm going to keep this. Because then the next thing that we're going to do is take the instantaneous rate of change, and that'll be the marginal cost, and then we're going to plug in 40 and see what is the instantaneous rate of change in 40 at 40, because that would be a way to estimate the cost of producing one more sailboat. So this won't be exact, but if I had the marginal cost generally as a function instead of just finding it at 40, then I'd be able to do this for any value, right? And so it would be faster. So I'm going to do the instantaneous rate of change at 40. So the limit as h goes to 0 of C of 40 plus h minus C of 40 over h equals I could say minus 1175 here, maybe. Save some time because we already did that. It doesn't actually necessarily save time, but it saves space. So 575 plus 25 times 40 is 1,000. $40 plus h squared is 1,600 plus 40h plus 40h plus h squared, minus 1175. Sorry, that looks terrible. Equals the limit as h goes to 0 of 1575 plus 25h minus 0.25 of 1600 is 400. 0.25 of 80 is 20. And then 0.25h squared. And then also minus 1175. Equals Okay, so I have 1575 minus 400, that's 1175 minus 1175. All of those constants go away. 25h minus 20h, and then minus 0.25h squared. Cancel those. That was my entire goal, was to be able to cancel that. So I now can plug in h equals 0, and this is 5. So before, we had 4.75. That was our actual, right? And then we end up with 5 by doing this marginal cost. Typically, production levels are higher, and so the numbers are kind of closer together than this. But even in this case, if your question is how much will it cost me to make one more boat, and I say about $5, if the real answer is $4.75, I think you're okay with me. And even if the exact answer was $5.25, I think it'd still be about $5 would still be correct. So this is how we use marginal cost instead of calculating difference to find an estimated cost per the next unit. So that answers that. Let's see, okay. So this is the last one. So the profit in hundreds of dollars from selling X items is given by 2x squared minus 5x plus 6. And we want the average rate of change going from 2 to 4. So this is not producing the next item. This is what's the average profit per item for the third and fourth items. So this is a little bit different question. We will probably be a little bit more wrong because of that. But then we're going to find the marginal profit at 2 as well. Okay? So the first question, what's the average rate of change? So we want profit at 4 minus profit at 2 divided by 4 minus 2. There are 2 items there. So this is, I plug in 4, and I get 2 times 16 minus 5 times 4 plus 6 minus 2 times 4 minus 5 times 2 plus 6. That's all over 2. So 32 minus 20 plus 6 minus 8 plus 10 minus 6. And you can just calculate P of 4 separately and P of 2 separately. 12, 18, 10, 20 minus 6, I believe is 7. So I hope I didn't make an arithmetic error, but now we want to do marginal at 2. Okay? So the limit, as h approaches 0, P of 2 plus h minus P of 2 over h, so P of 2 plus h is plus 2h plus 2h Okay, so combining like terms, we have 2h squared, 8h minus 5h, 8 minus 10 is negative 2 plus 6 is 4, and then P of 2 Okay. So the limit as h goes to 0 of 2h squared plus 3h plus 4 minus 4 over h. So I just plugged in p of 2 plus h there and p of 2 there. So the 4's go away, and we have 2h squared plus 3h over h. And then I plug in h equals 0, and I get 3. So you would predict the cost of the next unit to be 3 based on this. And of course, we did it from 2 to 4 instead of just 2 to 3, and we got ourselves more off. Which apparently I don't mention here. So, no, that was wrong. So what I have here is a parabola. And so the difference in the instantaneous rate of change here and the slope between 2 points like this is pretty different. The 2 is pretty, well, I'd have to factor that to find where the 2 is. But at any rate, once you get quadratic, if you make jumps like that, you end up pretty far off. So that's how we ended up off. But if we are just looking at the change from 2 to 3, and then we look at the instantaneous rate of change at 2, it wouldn't be as far. So you have to be kind of careful how you use these things. So that's the end of this, and I don't know when I'll send out the next one, but I will send this one shortly.